welcome to this talk on parallel batch dynamic trees via change propagation. I'm Dan, and this is joint work with Umut Ajar, Guy Blalock, Lakshman Dulipala, and Sam Westrick. So today we'll be talking about parallel algorithms for the dynamic trees problem. So we'll start off by going over some preliminaries. We'll talk about models of computation. We'll describe what the dynamic trees problem is and what the batch dynamic trees problem is. We'll talk about parallel tree contraction and rake-compress trees, which are some important ingredients in the algorithms that we're going to talk about. Then we'll talk about parallel change propagation, which is a technique that we need to develop in order to create our parallel batch dynamic trees algorithm. And then finally, we'll talk about how we can apply parallel change propagation to parallel tree contraction in order to obtain our parallel batch dynamic trees algorithm. Okay, so first of all, since we're talking about parallel algorithms, we need to talk about a model. Now, we're not really going to talk about any low-level details, so details of the model aren't super important. For simplicity, we'll work in the PRAM model. So the PRAM has P processors that operate in lockstep, and they read and write to a shared memory. We're going to use the CRCW PRAM, so we can have concurrent reads and concurrent writes. Then we need to have measures to analyze the effectiveness of algorithms. So we'll analyze algorithms in terms of their work, which is the total number of operations that they perform across all processes, and the span, which is the length of the longest chain of sequentially dependent instructions, which you might know as parallel time in some other models. So the dynamic trees problem is to maintain some forest while adding and deleting edges from it. Adding edges is often known as the link operation. Deleting edges is often known as the cut operation. And of course, while we maintain this forest subject to these updates, we want to support some kinds of queries, the simplest being connectivity queries, which allow us to ask whether a pair of vertices U and V are connected, i.e. is there a path between them, and more complicated queries, like given a pair of connected vertices U and V, what is the weight of the heaviest edge on the path that connects them? Or, given some way of routing the tree, what is the sum of the weights of all the edges in a particular subtree? Now, there are many examples of dynamic tree algorithms, most of which, however, are sequential. There's link-cut trees by Slater and Tarjan, Euler-Tour trees by Hensinger and King, top trees by Alstrup et al., and rake-compress trees by Ajar et al. In the parallel setting, we can make things a little bit more interesting and talk about what we call the batch dynamic trees operation. It's very much the same as the dynamic trees problem, except now we want to insert and delete edges in batches. So we want to update multiple edges at the same time, either by inserting a batch of k edges or deleting some batch of k edges. We'll call these the batch link and batch cut operations. And the goal is to support these operations in low work and span relative to the single update sequential algorithms. So all of the sequential algorithms mentioned on the last slide perform all of their operations in log n time per operation, where n is the size of the tree. One previous bit of work on batch dynamic trees are the so-called batch parallel Euler-Tour trees by Tseng et al., and they support batches of k edges in just k log 1 plus n over k work and log n span. Note that this work bound is very good. If the batch size k is small, then it's roughly log n work per edge, which matches the work performed by the standard sequential algorithms. However, if the batch size becomes large, then the work per edge tends towards constant. Say if k is n, then we perform just constant work per edge, which is better than the work performed by the standard sequential algorithms. The downside of batch parallel Euler-Tour trees, and Euler-Tour trees in general, is that they typically only support subtree queries. So the question on our mind is, can we match this nice work bound while also supporting a lot more general queries? To do so, we're going to need a few ingredients. We're going to look at rake-compress trees, which are one of the sequential dynamic tree data structures mentioned earlier. Rake-compress trees are based on an idea called parallel tree contraction, introduced by Miller and Reif. Tree contraction takes some input tree and then produces a sequence of smaller contracted trees each one consisting of the vertices of the previous tree with some independent subset of them removed. In particular, the way the tree contraction algorithm works is by applying two operations, rake and compress. The rake operation removes a leaf from the tree, while the compress operation removes some vertex of degree 2 and merges the neighboring edges together. Parallel tree contraction then consists of applying rounds in which rake and compress are applied in parallel to some independent subset of vertices in the tree. Ajar et al. Then design rake-compress trees by applying a change propagation algorithm to parallel tree contraction. Essentially, they come up with a dynamic version of parallel tree contraction, and then they use this to design a dynamic tree data structure that can handle path queries, subtree queries, and non-local queries, which are things such as centers, medians, and distances to marked vertices, etc. As an example of what rake-compress trees could do, we'll first have a look at tree contraction. Here's an example tree, and in each round we'll just delete some independent subset of vertices using rake and compress. So you'll see all the leaves get removed and some vertices of degree 2 get removed. And then we repeat this for several rounds until the tree becomes a singleton. At this point what we have is a sequence of smaller trees. Now, how does this enable us to come up with a dynamic tree data structure? The key idea is in interpreting the tree contraction process as being a recursive clustering of the vertices and edges of the tree. Each time a vertex is deleted, we can imagine that what happens is that vertex simply merges the surrounding clusters, where we can imagine that each vertex and edge is initially a singleton cluster. So in the first round, we note that the vertices are deleted, look like this, and we can imagine that they form a cluster with the edges surrounding them. In the following round, when more vertices are deleted, we can imagine that they then merge the adjacent clusters, forming more clusters like so. We can then repeat this, again merging adjacent clusters into one large cluster, and repeat until we end with a single cluster that encompasses the entire tree. What we end up with is a nice top-down recursive clustering of the tree. And since tree contraction performs just log n rounds with high probability, this clustering will have a depth of just log n. It's then by annotating these clusters that we can perform interesting tree queries like path weights, subtree weights, and non-local queries as described before. Applying a change propagation algorithm to this whole process then dynamizes the whole thing and gives you the dynamic tree data structure that we call rake-compress trees. So finally, just a quick overview on what I mean when I say change propagation. Change propagation is a technique for automatically dynamizing a static algorithm. So given an algorithm and its input, the algorithm is ran and the dependencies between the computation and the data are recorded. Specifically, this means recording the dependencies between who wrote to what variables and who read from what variables. When the input data is changed, change propagation can then selectively rerun just the parts of the computation that depend, i.e. who read, values of data that was changed, while parts of the computation that did not read any data that has changed does not need to be rerun. This is much more efficient than just rerunning the entire computation from scratch if only a small amount of data was changed. Now let's talk about our framework for parallel change propagation. We'll apply this framework to the tree contraction algorithm of Miller and Rife to obtain our batch dynamic trees algorithm. First of all, most frameworks for change propagation operate on some restricted class of algorithms. In our case, we work with what we call round-synchronous algorithms. A round-synchronous algorithm is a parallel algorithm that consists of m processes or machines. The algorithms perform sequential rounds in which each of these processes/machines executes some independent computation. These machines all execute in parallel. We additionally allow processes to retire, at which point they won't execute in any subsequent rounds. These processes all have access to a global shared memory, but we restrict them so that they can only write to each location in shared memory once, and they can only read values that were written in a previous round. We say that the input to the algorithm is the initial contents of shared memory. This model overall is very similar to Valiant's bulk synchronous parallel model, the main difference being that instead of having explicit communication channels between the processors, we use a global shared memory instead. The high-level idea of change propagation is then very simple, and it more or less does exactly what you would expect. We run the initial algorithm, and we record the following pieces of information. For each round and process pair, we record the set of memory locations that were read by each process in each round. We record the set of memory locations that were written to by each process in each round, and we record the set of processes that retired in each round. Then we record separately for each memory location in the global shared memory the set of processes that read that memory location and in what round they did so. So these things are all recorded during the initial run of the computation before making a dynamic update. A dynamic update then consists of changing something in the initial state of the global shared memory, i.e. it's updating the input to the algorithm. We then call the round process pairs affected computations if either that process runs in that round in one of the input configurations but not the other, which would happen if the process decides to retire at a different time in the two different configurations, or if a process runs in both rounds and both input configurations, but it reads some variable that has a different value than it had in the other invocation. Change propagation then consists in simply identifying and re-executing all of the affected computations, which roughly works as follows. We re-execute the computations in round order. We track which computations retired at a different time than the previous invocation. That is, they either retired last time but didn't this time, thus staying alive longer, or they retired earlier this time and thus stayed alive for fewer rounds. Then, for each round in order, we can determine the affected computations by looking at which shared memory locations have been modified. We can then update the tracked reads and writes. We can re-execute all of the affected computations, except of course those that retired early. Update the tracked reads and writes again, and then we can repeat, using any newly modified memory locations to determine the next round's affected computations. Then we can analyze algorithms that we put under the change propagation algorithm. In order to analyze the effectiveness of change propagation, we need a notion which we call computation distance. Given a particular algorithm, when ran on two different inputs, the computation distance is just defined to be the total work performed by all of the affected computations. You can think of this as being essentially the absolute minimum work that must be performed in order to perform the update. Then we have the following theorem about the efficiency of change propagation. If we let W delta denote the computation distance induced by a dynamic update, and then we denote by W, S, and R respectively the maximum work, span, and rounds performed by the algorithm, then we have that running change propagation on the dynamic update costs just order W delta plus R work and order S plus R log W span. Note that the work is nearly minimal, since W delta is work that must be re-executed in order to update all of the affected computations. And note that the span is also quite close to minimal. In the worst case, where R is equal to S, it's just log W span worse than the optimal span of S of just rerunning the algorithm. Now that we have our framework for change propagation, all that remains is to analyze parallel tree contraction and show that it can be dynamized efficiently. We can start by looking at the original analysis of Miller and Rife. They showed that parallel tree contraction takes just order n work and log n rounds and span with high probability. All this leaves for us to do then is to analyze the computation distance resulting from a dynamic update when we insert or delete a batch of edges. Ajar et al. Approached this in the sequential case, where they showed that the computation distance of inserting or deleting just a single edge is order log n. In our work, we explore the batch case. We show that given a batch of k edge insertions or deletions, the resulting computation distance from the dynamic update is order k log 1 plus n over k in expectation. This exactly matches the bound of batch parallel Euler-Tour trees by Tseng et al. So let's look at the intuition of how we'll prove something like this. First of all, in the round-synchronous framework, each computation corresponds to a vertex. We have to think about how we would implement parallel tree contraction as a round-synchronous algorithm. It's rather simple using this idea. Each computation is a vertex, and at each round, the vertex just makes a decision of whether or not it should be deleted, and it makes this decision entirely locally. It only has to look at its neighbors, and possibly its neighbors' neighbors, to determine whether or not its neighbors are leaves. Each vertex simply has to tell if it's a leaf, in which case it can be deleted, or if it's a vertex of degree 2, in which case it can be deleted. The algorithm then uses randomized coin flips to break symmetry in the case of a path of multiple degree 2 vertices. So based on this information, since tree contraction is entirely local, we can first deduce that if we modify k edges, this can affect at most k vertices in the first round. Note then that vertices can spread their affected status to their neighbors in each round. The problem in front of us then is how we bound the number of affected vertices, since it seems intuitively like if affected status can spread from neighbor to neighbor, the entire tree could become affected very quickly. To counteract this, we imagine grouping the affected vertices into order k connected disjoint subsets. In particular, we define the groups based on which initial affected vertex from the first round spread to each vertex, breaking ties arbitrarily. Within each group, we then call a vertex a frontier if it's affected but it has an unaffected neighbor. Note that the frontiers are the vertices that can spread. We then have the following key lemma, which is what allows us to bound the number of affected vertices. Our lemma is that there are at most 2 frontier vertices per group, and at each round, at most 2 new vertices become affected and added to each group. And this simply follows from the fact that affected status can only spread when a vertex is deleted. Remember that vertices are deleted in one of 2 ways. Either the vertex is a leaf, in which case it rakes. In this case, the only vertex it can affect is its neighbor. Hence, the number of affected vertices is preserved and only 1 new vertex is affected. Alternatively, a vertex can compress. If that vertex initially had no affected neighbors, then it affects its 2 neighbors. Otherwise, if it had an affected neighbor, it simply affects its 1 unaffected neighbor. In both cases, we create at most 2 new affected vertices, and the number of affected vertices that are frontiers remains at most 2. So, since there are order k disjoint subsets of affected vertices that are growing, and only 2 new ones become affected per group in each round, we can conclude that there are at most order k new affected vertices in each round. Now we can go back to the Miller and Rife analysis, who showed that with high probability, the number of vertices shrinks geometrically in each round. Now, since we're adding order k new affected vertices in each round, this is essentially counteracted by the geometric shrinking, since this applies both to affected and unaffected vertices equally. So by adding order k new affected vertices each round, and then shrinking the total number of vertices affected and otherwise geometrically, the total number of affected vertices per round remains bounded by order k in expectation. We could stop here and simply obtain a computation distance of k log n in expectation, but we can do better. Let's imagine splitting the rounds of the algorithm into the first order log 1 plus n over k rounds and the subsequent rounds. Based on the previous analysis, since there are order k affected vertices per round, within the first order log 1 plus n over k rounds, there are at most order k log 1 plus n over k affected vertices in total. Now, we can once again use the Miller and Rife analysis and the fact that the number of vertices shrinks geometrically in each round to show that after order log 1 plus n over k rounds, there are at most order k vertices left alive in total in the entire tree in expectation. Followed by the fact that the number of vertices is shrinking geometrically, there are at most order k vertices left alive in total in all subsequent rounds. Adding these up, we can conclude that there are at most order k log 1 plus n over k affected vertices in total in all rounds across all of the rounds in expectation. Therefore, we can deduce that the computation distance is at most order k log 1 plus n over k in expectation. The work bound therefore matches that of batch parallel Euler-Tour trees. But we can then put everything together. We can then use our change propagation algorithm and deduce that we can support batch insertion and batch deletion of a forest of size n in order k log 1 plus n over k work in expectation and log squared n span with high probability. Using the Rake-compress tree framework, this dynamized tree contraction algorithm can then be used to perform dynamic tree queries on the tree as it undergoes batch insertions and batch deletions. This essentially gives us a parallel version of Rake-compress trees. And since Rake-compress trees already support path queries, subtree queries, and non-local queries like centers, medians, and distances to marked vertices, our data structure automatically supports all of these queries too, in the same time bounds. And this improves upon the batch parallel Euler-Tour trees, which only supported subtree queries. Thanks for listening, and let me know if you have any questions.